All right, cool. Whoop. Anything else from homework stuff? I mean, I will come back and do an example like that once we do the terminology. Anything else from homework stuff? Okay. I will say one thing, bless you, about a problem I should be getting questions about. There's a problem about like Latino voters and California voters and stuff like that. There's two problems that are sort of in the same vein. So if I told you 87% prefer chicken, and of those who prefer chicken, 10% like rice with it. Let's make up some stuff here. How do you capture those ideas mathematically? And really what that means is, what symbols do you use to capture those ideas? And you're all like, I don't freaking know. So what's the probability somebody, what do you want to use for the probability of chicken? I don't know. What letter do you want to use here?
C.
No, what? So what's probably somebody who likes chicken?
0.87.
0.87. So if you have a formula that requires this, now you know what the hell to put there. How do you write this one? This is kind of cool. There's a hidden word that tells me which symbol to use. Of those. What's that related to?
Given.
Given. So given what? What do we know about the person in this sentence?
They prefer chicken.
They prefer chicken. Of those who prefer chicken. Okay, I'm only talking about those people that prefer chicken. So given they like chicken, 10% like rice with it. Do you guys, this is unbelievably important. Everybody messes those problems up. They're not sure what to do with the big paragraph. There's a big paragraph with some percentages sprinkled around in it, and then they ask you questions, and you're like, huh? But if you rewrite what the percentages relate to in symbols and write the formula for what they're asking you, you just plug this stuff in the right place. This is just like algebra. You had to know what X was and what Y was, so you put stuff in the right place. So this would be, wait, one up. I like it. So then, if I ask you, what percentage of people like rice and chicken? What's the formula for R and C? So you can just throw in what you know now. The formula for R and C is the probability of C, that's probably of R given C. And then you can just throw that stuff in there. Yay. So this is exactly the way two of the problems in the homework kind of work. Big paragraph with some percentages sprinkled. You got to write each percentage with a symbol that represents what it means. And then you write the formula down, put them in the right place. That's a very simplistic, oversimplified view of how math works in general. Okay. Anything else from homework before I go into the terms that relate to the question from earlier? Okay, all right. I'm an optimistic fool. So I'll take that means that it's all going well. So the first idea is the idea of mutually exclusive. When I say the word exclusive, what comes to mind? Separate? Sure. Doesn't include everybody. It excludes some people, right? It's an exclusive club. What does that mean? Yeah, only certain people can get in there or something, right? I like it. So exclusive excludes. So if I combine that with the word mutually, what does mutually mean? If something's mutually beneficial, it's going to benefit both of us. Mutually exclusive means you can't come in this club and I say I don't want to go in that club. Right? I mean, we mutually exclude each other. Club says I don't want you, and I say I don't want you either. So mutually exclusive in statistics, in probability, are two events that cannot occur at the same time. I used to use an example about a cat and a dog. This is a long time ago, by the way, because then cat dog came out. Have you ever seen cat dog? I don't want to go into the biology of this creature, but couldn't really use that anymore because there was an animal that was both. That sucked. Then I was using rocks and salamanders, and there's no rock salamander. You know, didn't want to use rock and lobster. But, so if I walk into a room and there's rocks and ice cream, right? Rocks and ice cream. And I am blindfolded. And I pick something up. What's the probability I just picked up something that is rock and ice cream? It can't be both, right? You can have ice cream that looks like a rock, but is it a frickin' rock? No, it can't be both, right? Unfortunately. I'd love it if I found the volcano that spewed out beautiful, yummy ice cream. That'd be awesome. But why? It would have a whole other dimension to it. But mutually exclusive means that the probability of A and B, the probability they occur at the same time, is 0. So if in the homework it says something like J and M are mutually exclusive, you immediately write down probability J and M equals 0. And then you can use that anywhere you need to. I love it. So, for example, are Democrat and gun owner, are they mutually exclusive? No, they're not. They're not mutually exclusive. There are Democrats that own guns, right? Are you guys semi with me? So to find something that is truly, so Jack and clubs, obviously not, but Jack and 8 in a deck of cards, right? If you have a card that's a Jack and an 8, I'm not playing with you. Oh, full house. No. So no, that would be mutually exclusive, those two. You guys doing all right? So if I told you, example, C and W are mutually exclusive events. Find the probability of C given W. What's the formula? And you're allowed to look back through your notes. There's no quiz out there. What's the formula for the probability of C given W?
Probability of both of them is your probability.
In this case, I like it probably W. Now, when you read the homework and they tell you this and they ask you to find this and you write this down and you say, they don't tell me anything. What's this tell me immediately by itself?
Probability of C and W.
Yeah. Is?
0.
0. Therefore, 0 over who cares? We're assuming W can happen. Or else you get a very interesting dilemma, but anyway. Oh, no, don't worry about it. That doesn't really work here because we don't have functions, really. But I appreciate the attempt. It would be indeterminate, yes. It would be a different story. You guys with me? I mean, that idea of mutually exclusive by itself, very simple. The two can't happen at the same time, so the and is going to be 0. But then how do you use that information? Well, there are many formulas that rely on this piece. And if that's 0, they're going to be easy. You just don't want to miss this. The first sentence is very important in those problems. All right, so mutually exclusive is the one that isn't that terrible. So let's get into the other one. And this isn't that terrible either. It's just one of the most frustrating things in my teaching career is for people to really understand this idea. It's a different idea. It's not that hard. And I'm sure I'm really not making you anxious at all. Let's see. It's the idea of independence. All right, so let me ask you this. Okay, let's see if I can come up with something less controversial. Okay. So let's say, screw it, I'm going to go for it. Let's say you see somebody walking towards you in the distance. They're pretty far away. So I can't even tell if they're a man or a woman yet. They're really far away. They sort of have long hair. There's just no way to know. So it's probably they're a woman. 50%, right? You with me? It's not saying anything about that. We're just too far away. Now, here's the part that gets me in trouble sometimes, and I don't care. Let's say that you noticed that they had just gotten off a motorcycle. Is the probability that they're a woman the same as it was before? No. Are they more likely to be a man or a woman? They're more likely to be a man. Now, I love it. One semester I said this and somebody got really upset at me. I am not saying that women do not ride motorcycles, am I? I am not. I'm talking about probabilities. Which one rides motorcycles more, men or women? Men. So is it impossible that it's a woman? No, that's not what independence, that's not what this whole idea means. Does the occurrence of one thing, them getting off a motorcycle, affect the probability of something else, them being a man or a woman? Yes, it does, right? Or let's say that you had a really late night and you drank a few too much. Does that affect the probability you'll get up in time the next day? Yes, so those would not be independent. The probability you get up would depend on what you did the night before. Doesn't that sound all too familiar, and it makes sense? Yes? I like it. Maybe. In fact, some of us that aren't here might be living that situation right now. I don't know. So let's see. The hard part of this is connecting this to math. Connect that idea to the math and not forget why it makes sense. So what key word about probability does it sound like is inherent in this kind of situation? The probability you get up any morning is something. If you stayed up late, drank a lot, whatever, the night before, that probability changes. What does that sound like? What probability word is in there? Because I'm not just saying the probability you get up, I'm saying if you did something, what now is, okay, what does that sound like? Given. Given that this happened, does that change the probability of this other thing? That totally makes sense. The only way to check to see if two events are independent is to see how they affect each other. You can't say anything about each probability separately. That doesn't make any sense. The idea of independence is all about, does one affect the other one? So what probability includes the idea of an effective one on the other one, the given? Yeah. So to be independent, and this goes both ways. If you know a little more math, this would be an if and only if. What does that mean? That means this goes both ways. So to be independent, this must be true. Now look at what this says. The probability of A given B. So given that B happened, did A give a shit? No, it stayed the same. So if this probability is the same as what the probability of A by itself was anyway, then B did not affect it. Please let that make sense. So how does that look concretely? Well, let's see. Let's do an example. I'm going to have to use cards just because I want to. So deck of cards. How many suits in a deck of cards? 4 suits. There are hearts, diamonds, spades, clubs, green clovers. No. How many cards in each suit? 13. I like it. And they all go ace through king if you assume ace to be 1. So there's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king. I like it. So let me ask you this. If I pick one card, what's the probability it's a king? How many total kings are there? 4. There's a king of hearts, a king of diamonds, so forth. So there's 4 kings out of 52 cards. So somebody help me out, what is that? That's 1/13. $0.769. Now, let's make this more interesting. Let's say that this is a card game where you put money, you bet money on what card. I pick a card and you put money down. So let's say you put money down on the king. There's only like not even an 8% chance you're going to win, right? And this is, of course, pretty good odds for gambling. But I give you a chance to ask a question to see, let me see, to see if you want to put more money down on it being a king or not. All right, it's a weird game. So you could ask, is it a king? And then if I say no, you're screwed, right? So it doesn't really help you figure out, and then you're like, let me just stay there. So let me see, what if you asked, is it a club? So I've got a card that I've picked. I'm looking right at it. You've got money on it being a king. And you really want to ask a question to gauge, is the probability different than what I thought? There's an 8% chance you're right. So you ask me, is it a club? And I say, yes, it's a club. So what's the probability now that it's a king given, because I just told you it's a club. It is a club, yes. I tell you, yeah, it's a club. Does that affect the probability you're going to win? How many clubs were there? 13. Out of those 13 clubs, how many are a king? 1, which is exactly the same thing. You have no real new information. It did not change the probability at all. So are the events king and club independent? Yes, because the probability of one given the other is the same as the probability one was to begin with. So knowing it's a club did not affect the probability it's a king. I should call that independent. That just makes English sense, right? What do you call two things that don't affect each other? Independent, right? I guess. So sometimes math people, we pick words that make sense. A lot of times we don't. I know. I'm sorry for that. So what if you asked instead, is it a face card? Now, how many cards have a face on them? We got Jack, Queen, and King can be staring at you, judging you, right? How many total cards is that then? We have 4 suits. Say again? Do it again.
Are you not counting aces?
An ace has no face. I know it rhymes. There's no little ace dude looking at me. So Jack, Queen, King are the cards that have an actual face. They could have 1 eye or 2, and I'm not anybody that could speak to that. But you guys with me? 1 eye Jack. So what's the probability that it's a king given that it's a face card? And I tell you, yeah, it's a face card. Yeah, it's got a face on it. Well, how many cards have a face on them? 12. 3 for each suit. And out of those 12, how many are kings? Still 4, yeah. Why was this one? Because we threw out the king of hearts, the king of diamonds. We threw out all those kings. Here I didn't throw out any kings. So that becomes a 1/3 chance. It's 0.333. That's much higher than what it was. Right? That's over 4 times the probability of winning. So maybe if I'm a true gambler, I put a little more money down there. I feel pretty good about it. Maybe. So with this, our king and face card, are they independent? No, because knowing it's a face card, did it change the probability it was a king? Yes. So if I ask you, are A and B, whatever the hell they are they independent? The answer must include mostly math. You can't just write a little paragraph, well, you could be that. No. It's a mathematical idea. Is the probability what it was before the same as or different from the probability it is now? Knowing this other thing. That's what you check. Okay, now, one last idea, and then I'm going to unleash you on this worksheet. Okay, so there's mutual exclusive. The and is 0. Independent means the given stays the same. Okay, I like it. And just real quick, before we leave these ideas, I want to show you something. What is the probability of A or B in general? What was OR basically? OR is basically addition. I love it. So the formula was, and the reason we say basically is because you don't just add them, you have to. Yeah. If A and B were mutually exclusive, MUT X. If they were MUT X, then what happens?
The last part goes away.
Yeah, so then they are truly just additive, right? You just add them. So if they're mutually exclusive, that's the one time you can just add the two probabilities together. And here's something we already know. What time is it? Probably A and B equals probably A times probably B given A. If B and A are independent, what happens? If they are independent, what does that mean is true about the probability B given A? They, what they? They, what they? So what's probably B given A equal to if they are independent? Given that A happened, does B give a shit if they're independent? No. So probably B given A is the same thing as the probability of B. The probability of B, given that A happened, doesn't change. Please let that make sense. It's independent, so if A happens, does B care? No, it stays the same as it was. So what's the one time I could just multiply two probabilities together? Is if they're independent. We already know this. This is what we do when we pick the dude out of a haunted house and then the next dude out of a haunted house. If I put the first dude back, the second probability didn't change. I just multiply the two probabilities directly. When did I have to change this? Is if I didn't put them back in. It was not independent then. It depended on who I picked first. So we've actually done this idea before, we just didn't call it what it is. Okay. I love you guys. Yes? Oh, beautiful, of course. Two lines. They could be parallel. They could be perpendicular. And they could be all this other shit, right? If they meet, they're not parallel, but if they don't meet at 90-degree angles, it ain't perpendicular either. So you got a lot of shit that is neither one of these. Neither mutually exclusive nor independent. Please understand that. In fact, all right. If two things are mutually exclusive, they are the most dependent you can be. What the shit? So if I walk into a room and I've got rocks and ice cream. A bowl of rocks and a bowl of ice cream. I've got like 8 of each. You with me? You with me? Is that a mutually exclusive thing to probably pick up a bowl of rocks? Can I also pick up a bowl of ice cream at the same time if I only pick up one bowl? No. It's either rocks or ice cream. I can't. And then I got to like, some weird ass fear factor thing coming back. Right? So that's a mutually exclusive thing. Are you with me? It's either rocks or ice cream. It ain't both, unfortunately. Now, if I am blindfolded and I pick up a bowl, what's the probability it's a bowl of ice cream? I got 8 of each. So it's probably a bowl of ice cream. 50%, right? If I got equal amounts of each, it's 50-50. I got a 50% chance it's ice cream. I dip my spoon into it and it's a rock. It's rocks. So what's probably it's ice cream now? It's freaking rocks. What's probably it's ice cream now? 0. So if you have mutually exclusive events, they cannot happen at the same time. So they are definitely not going to be independent, right? Okay, that's a little freaky. I want to make sure you kind of are on the border of that question, which gets a little murky. You don't have to be one or the other, but there are ways to check which one you might be, if you are one of them. Okay, all right. So this is from earlier. If A and B are mutually exclusive, like the ice cream and the rocks, what's the probability of A given B? Given that it's rocks, it's ice cream. Well, what goes on the top of that? And since they're mutually exclusive, that top is always going to be 0. So that's very interesting. If you are mutually exclusive events, that's the most dependent you can be. The minute you know one of them happened, the other one's probability dies. Whatever the shit it used to be, there's no chance now. So a teacher, I know I got an F, but what's probably I can get an A? It's a leave. Right. You with me? You understand? A little bit? All right. You didn't like my joke about the grade, but it's okay. One last thing. That was me still going on with this. So this is an interesting thing about large populations. So here's an example of a small population. If I have 4 red poker chips and 6 blue poker chips, right? Stay with me for a second. We've already done this kind of thing. If I pick 2 poker chips without replacement, let's probably get a red and then a blue. Just a nice little review. So do it without really pick one, throw it away, and then pick another one. Let's probably get a red and then a blue. And of course means what operation?
Multiply.
Or is basically add.
Multiply.
And is basically multiply. I love it. That's not enough to do specific problems, but it's a really good general thing to remember. So what's probably the first one's red? I'm going to put my 2 little hangman spots there. Probably first one's red is 4 out of 10. I throw that away. 6 out of 9. I love it. And then whatever the hell that is. 2/3, 2/5, 4/15, which is like 0.24 or something. 0.226. I went the wrong way. Man, Jeff. All right. All right, that's old news. So you notice how I had to know the total and then I adjusted numbers as I went. But let's talk about this instead. Let's say that my population is all Americans. I put all Americans in a bag. And we're just jostling around in there. I love it. I'm an alien species. I just collect all the Americans up in a bag and say, this should be yummy. And take it back to my home world and have some lunch. And let's see, how can I break Americans down into two camps without being too controversial? I don't know. Let's say Californians and not Californians. So let's do this. Let's not do Californians. Sorry. Let's do something that we know for sure, something about. So there's 11% of these people are left-handed. So there's 89% not left-handed. You guys with me? All right, I like it. So I'm not sure what the percentage of Californians is, to be honest. How many Americans are there? There you go. 350 some odd million sounds about right. I remember when we passed 300 million, and then we just kept going. Are you guys with me? How does that number relate to the math we did here? Where would that number show up?
In the total?
Yeah, in the bottom, in the total. I love it. That's a really huge population, right? And I'm going to pick 2. Is that a large sample compared to my population? Pick 2 Americans. Is that a large sample compared to my population? 2 people versus 350 million, right? That'd be a quick fight if I did a fight thing. Unless they're 2 Hulks, I don't know. And I ask you, what's the probability that I pick a left-handed person, lefty, and then not lefty? Why don't I just say righty? Because somebody could be ambidextrous and all that kind of, ooh, that's nice for you. Right? Huh? Or if they have 1 arm or no arms, we would just call them not lefty. Right? So that picks up every other possibility. All right, now stay with me now. Now I could be sort of insane. Now, on the bottom I would put, let's say that 350 million is correct. What would go on the top? Let's see, you guys.
11%.
11% of that, right? What's 11% of 350? 35.5, 38.5 billion. All right. Here, I desperately need you. We're not going to do it like this in a minute. Do you understand? I'm trying to make a point right now that this is really silly when I have such a huge denominator, and it's going to change by how much for the next probability? 1. So now what do I have on the bottom? Times 349, 999, 999. And then on the top is going to be, what would it be? 350 minus that. Blah, 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 blah. That's not gonna change the probability by much at all. When you have a large population and you're just taking a few, 2, 3, 4 people or something from it, you don't have to do it this way. Thank God. Why do we have to do it this way here? Because 4/10 versus 4/9 is a decent difference. They are different enough to have to be careful about. 4/10 is 0.4. 4/9 is 0.44444. That's 4% difference. That's kind of a large difference. When I'm talking out of 350 million and then it goes down by 1, that's not going to change the probabilities that much. So screw this way. What I'm going to do then, what's probably a lefty? 11%. What's probably not a lefty? 89%. Just use the percentages directly. That kicks so much ass. When am I allowed to do that? I could get very specific and say it's when your sample is less than 5% of your population. But basically, whenever the population is large, you could do this. I like it. So for problems where you have less than 100 chips in a bag, you're going to have to do it where you keep track of all the ratios. When you have 300 million people, we're talking about, nah, just multiply the percentages. Okay, maybe. Yes? But just whatever the hell 0.11 is plus 0.89 is. Yeah. So 0.089 plus 0.0089. 0.89. Point. No, he's going to help me. Okay. 0.089. 0.97. Something? 9. Thank you so much. Okay, so let me finally shut the hell up. Let me give you guys